Welcome to the STEM Pathways with Rohan Sharma podcast, where we dive into the exciting world of science, technology, engineering, and math. In each episode, we share exciting stories, groundbreaking research, and inspiring interviews with experts and enthusiasts who are pushing the boundaries of innovation. Whether you're a student, a professional, or just curious about how the world works, join us as we explore the endless possibilities of STEM. Let's get started. Today, I'll be interviewing Manos Tentzeris, who's a professor at Georgia Tech. How are you doing today?
Pretty well.
Yeah, so to get started, I wanted to ask what made you choose your major for your bachelor's degree?
That was an interesting choice. I was interested in math and understanding of nature. Since I was a little kid, I was uh, playing with some electronic circuits or some electronics my parents were using since I would say, like 6 or 7. Still, I want to choose a job that would lead to new inventions, new ideas, new applications. So a very important vestige of the job I want to follow was to prepare me to invent new things or new applications. And engineering was the natural choice. I have to say, Star Wars played a critical role. I was quite intrigued by tricorder teleportation and space exploration, and that further pushed me in this direction. So I had different options in my mind. Sometimes I was wondering, should I go to a more science related areas like physics or math? But I really like the applied aspect. I really wanted to see my devices to be used. And that's how I chose engineering. And electrical engineering was an area I chose because I figured out that could be used pretty much everywhere. So that gave lots of options whenever I would get deeper knowledge in some of the areas.
So, what was your experience like while getting your not only bachelor's but also master's and PhD degrees?
I was very interested. I got my bachelor's in Greece from National Technical University of Athens. I got a really solid foundation in math and physics that provide me with the tools to use for areas of interest. And also that exposed me to many different directions for electrical engineering. Participating in term projects and undergraduate research was a really critical aspect, and I highly recommend to all of you, don't stick with just coursework. Get involved. Get familiar with technologies firsthand. Get familiar with how new products, new ideas are coming out. And that helped me because getting involved in the microwave lab made me focus my electrical engineering studies to this area. Being exposed to the design of antennas, to the design of wireless devices, of rudimentary radar systems, even the first generation of wireless phones intrigued me a lot. And the use of simulation tools convinced me that this is not an undoable task. So I was quite happy focusing in the area of wireless and microwave and RF engineering. And that made me decide going for graduate school. Applied to different schools, and I finally decided to join University of Michigan Radiation Laboratory, initially to do masters. So I was not predisposed to doing PhD in the beginning. So I joined the lab, radiation laboratory, lots of very well-known professors, having developed very, very new technologies. Joined the lab, spent 18 months for my master's, and also putting together thesis, research thesis. Uh, and this research thesis left lots of unanswered questions. So that was a new idea. That was an idea of utilizing wavelengths or multi-resolution analysis, which is quite theoretical technique for the modeling of microwave. So in the beginning, I was like, am I interested in this? But I figured out that programming allowed me to start using it for practical circuits. So utilizing this technique as a mathematical microscope to zoom in, zoom out in really complicated circuits that could not be analyzed utilizing a piece of paper and equations. So whenever I was finalizing my code on this, I was like, there are a lot of things to be done. We may start using it not only in some simple circuitry, but maybe for whole systems. And that's how I decided, why not staying for another 3.5 years to do a PhD, focusing exactly on this. Had a really great time in my PhD, great advisor, really, really important. Professor Linda Katehi, my advisor, was an excellent inspiration, along with my even undergraduate advisor, who set up the foundation for my interest, Professor Uzunoglu. So these two people played a really significant role of me deciding to stay longer and staying for a PhD. Because I figure out good mentors provide not only some technical advice, but even some life advice. And that was very important. That made my PhD path very enjoyable. I have to stress, PhD is not a straight line. So somebody deciding to go for PhD has to be prepared for these ups and downs. But these brief moments of success are really, really rewarding if you really want to come up with new stuff, new ideas, and so on. So it has ups and downs, but that was very rewarding. And then at the end of my PhD, uh, when I had developed this new technique, this new approach, I started wondering, should I go to academia? Should I join a research lab? Should I go to one of the big companies? That was a big crossroads. And what really helped me was visiting some of the top universities, while also interacting with the industry in my publication extensions. So that gave me the idea to weigh the pluses and the minuses, and prioritize. I don't say that what I chose is something everybody should choose, because it's a personal choice. But what I really like in academia was it offered the freedom to research the direction that excites you. So on the one side, that's quite busy schedule. You have to teach classes, you have to educate young students, young intelligent students, you have to write proposals, but also you have this freedom to do what you like doing. In a sense, I would say joining the academia is making your hobby your job. And that's quite important in my opinion, because this way you don't really worry about difficulties, challenges, and you do your best. And then the other big thing I would say in academia is you get the opportunity to work with really intelligent colleagues. Because in my opinion, PhD or graduate school, it's pretty much a group of colleagues. So you don't have the typical company hierarchy, senior manager, junior manager, new engineers, and all this. So being involved in academia, you are providing advice to a group of very smart people, and you're really happy seeing these people blossoming and growing not only technology-wise, but also mentality and life-wise. And I would say, you asked me before whether I enjoyed my PhD. That was one of your questions. I would say what I realized during my PhD was that PhD is a very different degree than bachelors and masters. Bachelor and masters mostly have to prepare you for your future jobs. So it gives you exposure to a variety of topics. Bachelor's is quite a wide breadth of topics. Masters, you start getting deeper knowledge in some of these topics. But PhD is not just a course or technology degree, it's a life-changing degree because it changes the way you are thinking. It makes you think in a more analytical way, not only about technological problems, but also about your life problems. And makes you think from different angles. So that's what I appreciate for PhD, and also that's what I'm appreciating about my current job, to get this more well-rounded perception of life and technology as well.
So, you've been a professor for how long now?
I've been a professor since 98.
Mhm. And
98.
how has research changed since then?
The fundamentals are the same. Because there are different technological needs. But a very important point, especially in these high-tech topics, is tools are changing. So you have to keep yourself updated with new technological developments and integrate with your research plan. So I would say the fundamentals are the same. I'm working on wireless technologies, RF technologies, high frequency systems, and so on. So all of them obviously are governed by the same rules. These are like Maxwell equations. And also, I would say the fundamentals of the simulators are the same, despite the fact that the needs have changed. So we had the emergence or the proliferation of internet in the mid to late 90s. That was a big game changer because that allowed me to have a much more immediate access to the latest developments. And then in the mid to end of 2000s, 3D printing started to enable new designs or new approaches. And I would say the third disruptive technology is coming up nowadays, which is artificial intelligence and machine learning. But these are tools. So the fundamentals of an engineering job involve four major steps. Number one is identify the problem. So you're trying to solve a problem. I mean, we're engineers. We're not doing stuff just to do them. So we identify the major challenge or the grand challenge coming out. No matter whether it's going to be a new, faster communication system, a better, more sensitive sensor, or even Internet of Things or digital twins nowadays. Number two is to review what is the state of the art. You do not want to repeat a work that has taken years or 10 of years for other engineers to develop. Number three is figure out what is the best angle of attack. So choosing your tool, figuring out how conventional tools and also newer tools can help you come up with some solution. And the step number four is prototype. So don't be afraid to get your hands dirty. So make your idea in a prototype. And these are the fundamental steps. I don't think these steps have changed over my career. As I told you, tools have changed, problems have changed or evolved, and specs have become more and more demanding. But the approach has been very, very important. And another, I would say, extra step that you have whenever you are in academia is try to combine ideas from different disciplines. I mean, this is one of the main approaches in my career. So I'm an electrical engineer. But still, I'm combining approaches, for example, for civil engineer, for structural health monitoring, from material engineer, for new materials that would help my design, or new nanomaterials with better properties. Even from art. One of our areas we're working very lately is the area of 4D electronics, or morphing, or shape-changing electronics, quite similar to the transformers you see in the movies. So that involves origami ideas, art ideas. So don't be afraid to combine this. In my opinion, engineering is not a hermetic science, because especially in high school, and that's a big advice even for high school students who are afraid of STEM. It's not dry math. It's not just applied physics. I mean, your career, you will see, you can combine ideas from many different areas. Right now, electronic systems or engineering systems are not exclusively circuits or screws or steel and braces. They increasingly incorporate ideas from other areas, like art, as I told you, architecture, in addition to other domains of engineering.
So for my last question, I wanted to ask if you have one piece of advice for someone who's still in high school or early in college wanting to follow a similar career path as you.
I have an advice to not be afraid of STEM and engineering jobs. Engineering jobs nowadays are not just manual jobs. Keep in mind that engineer of the future and STEM of the future are some areas that can combine computer interest with some real problem solving. And now you have the tools to solve all these problems without resorting to really extensive math derivations or really extensive prototype. In the future, you're going to have unprecedented tools like artificial intelligence enabled 3D printers that could allow very, very new ideas to come into fruition. So don't be afraid of STEM and engineering. Be involved and be ambitious without fearing to apply out of the box ideas. Engineering jobs of the future and STEM jobs of the future will not be just incremental, because AI will do the incremental job, but it will allow your new ideas, your out of the box ideas, to become reality. So be involved. Don't fear STEM and engineering, and you're going to have a great career. But first of all, do what you like and what interests you.
All right, then. Thank you for joining me on the podcast today.
Thank you very much, Ron. I'll be happy to answer to any follow-up questions. Please feel free to distribute my contact or send me any questions from people watching your podcast. And also, I really want to thank you for this great opportunity to reach out to high school students. Engineering is a great area, misunderstood area, but I would say don't be afraid. I mean, lots of options, lots of exciting things to come.